Hi everyone, my name is Siamak and welcome to the ACIGS 2020 August webinar. We have a very interesting webinar today with Professor Jorge Zornberg from University of Texas. So it's 12 noon here in Australia, Eastern side, and it's 9 p.m. In Texas. And it's going to be a very interesting presentation. And then we have a presentation by Geofabrics, the sponsors of this webinar, at the end as well. I'll just take you through a couple of quick slides. You all know about the IGS as a global society, geosynthetics, International Geosynthetic Society with more than 45 chapters, and the Australasian chapter is where we are. So you are aware of the geosyntheticsociety.org. That is the website of the global society, and also ASIGS website, Australasian chapter of International Geosynthetic Society. The website address is ASIGS.org. And I want to just do a couple of quick announcements today. One important one is the 2020 ASIGS election. This year is the end of the 2-year term of the existing team, and we're looking forward to have the new team starting from 2021. So until end of August, we are asking everyone who's interested to join the ASIGS committee to submit the form. As you can see, that red circle is showing where you can find on our website the submission form for the election. So if you want to become an officer of ASIGS, make sure you fill that form out and submit it to us. Basically, the ACIGS encouraging any member who is interested in furthering the ASIGS mission to consider nominating for one of the positions. And I have two other announcements. One is the ASIGS webinar series anniversary, and those balloons over there are how we celebrate the anniversary of our webinar series. Exactly 1 year ago, in August 2019, was our first webinar, and at the moment there are lots of webinars happening, mainly because of the situation around the world. But ASIGS was one of the pioneers. I think we started a year ago, and on the left-hand side you can see we have made available all of the recordings of the webinars that we've done so far. So you can access to those resources from our website. The second big announcement is the results came out from IGS, the chapter survey reports, and the results showing Australia, ACIGS, Australasian chapter is amongst the top five chapters of the world. So this is a very great result, and I really want to congratulate the chapter, Australasian chapter, and the committee, and all of our members for the support, all of the company members for the support. And we have had a very successful 2-year term, 2019-2020, with lots of events and a lot of activities. So hopefully we have a very good new team starting in 2021, and we keep the momentum and move forward with more success in the future. Last thing is the certificate of attendance. We have been providing this upon request, so you won't automatically receive a certificate of attendance. But if you attend any of our webinars or any of our other events, and you require that, request that basically through us, we can provide it to you for your own records. Today's webinar, we have Geofabrics as our sponsor for this event. So thanks to Geofabrics. And like I said, we have a short presentation, case study presentation by Rajesh at the end of this webinar. And the presenter, as I said, Professor Jorge Zornberg, one of the well-known names in the geosynthetics industry. So it's an honor for us to have Jorge on this webinar presenting about roadways founded on expansive soils. So as much as I know from this presentation, the first half of that will be characterization of the problem, and the second half will be about mitigating the problem with geosynthetics. A very brief introduction of Jorge. So basically, Professor Jorge Zornberg has over 30 years experience in practice and research in geotechnical and geosynthetics engineering. As an engineering consultant, he has been involved in the design of civil transportation, mining, and waste containment infrastructure. He has also served as expert witness in a number of litigation cases and forensic investigations. As a researcher, his focus has been on soil reinforcement interaction, geosynthetics, earth retaining structures, roadways, urban and mining waste containment, unsaturated soils, and numerical and physical centrifuge modeling of geotechnical systems. From 2010 to 2014, Professor Zornberg served as president of the International Geosynthetic Society, ACIGS. He has also served in leadership roles with the ASCE Geo Institute, currently chairing the Geosynthetic Technical Committee. He has authored over 400 technical publications, edited a number of proceedings and book chapters, and been awarded 3 patents. Professor Zornberg has been invited to deliver keynote lectures in numerous events around the world. Thank you, Professor Zornberg. Now I stop share from my end and over to you for starting your presentation, please.
Very good. Thank you so much, CMAC, for a kind introduction. It's for me such a privilege to be here from somewhere in Australia. It's so interesting that now we do not have a location, and we were just talking about that I'm presenting this lecture live, but since yesterday, Monday, 9 p.m. here in Austin, Texas. So
That's
can you
right.
hear me well?
Yes, everything works perfectly. It's Tuesday here in Australia, so we live in future, as I said. So thanks, Jorge, and yeah, over to you for your presentation.
Very good. So roadways founded on expansive clays. This is a problem that you have in Australia. It's a problem that we have here in the US, in particular in Texas. So what I'm going to do here is I'm going to talk about characterization of the problem. This is a very geotechnical aspect of the presentation. And then I'm going to get into how, once we know what the problem is, how to solve it using geosynthetics. All right, so what is the problem with expansive clays? Let's say that we have a road and the road is founded on expansive clays. It turns out that the expansive clays swell and shrink in response to the changes in moisture. So when the moisture content is high, the clay will swell. When the moisture content is low, the clay will shrink. And it turns out that the shoulders of the roads will change moisture very quickly or very often, while the center line of the road will not. Consequently, we will have that the shoulders will heave and settle, heave and settle. And as a consequence of that, mainly during the dry season, at the end of the dry season, we start seeing something like this. Very well-defined longitudinal cracks along the road. If you see this type of distress in the road, don't blame the traffic. If you see this type of distress in the road, you can start thinking of potentially you are sitting, or the road is sitting on expansive clays, and it can get really bad. This is a road nearby Austin, Texas, where I live. Sometimes we have this problem depending on the weather conditions, but sometimes we have this problem soon after opening the road to traffic. And these are other examples in Central Texas, in this particular case, in another big city in Austin, in Texas. in San Antonio. We call them the Badlands. So these are definitely, this is bad for roadways, and it's definitely something that honestly we do not design for. We design roads for traffic. We do not design these roads for environmental load. And this is not an exception. This is a very, very relevant problem. Let me show you some numbers. So what you have here is some data only from the US. We can consider that expansive clays and problems associated with expansive clays are some form of natural disaster, in the sense that they are caused by weather, typically extreme weather conditions. And we can see here that on a yearly basis, the cost associated with expansive clays exceeds 15 billion with a B, $15 billion per year. As a reference, here we have Katrina, Northridge. Some of these, as a whole, the costs, and this comes from actual data from insurance companies. The costs, the financial costs associated with expansive clays far exceed the combined costs in the US of all other natural disasters. It is true that expansive clays are not life-threatening, but when we're talking about financial losses, these are actually huge. And here we have where is geographically the problem associated with expansive clays. Here in blue in the United States, central US, we have locations where there is a significant portion of expansive clays. And here in red are the locations where, okay, this is really bad stuff. Do not plan on building your cities along in these red areas. But that's not what we did in Texas. Let me show you Texas, a detail. And here is what is called the Eagle Ford Formation, this red line here. And this is probably the most important highway along in north-south highway in the state. And here's Dallas-Fort Worth. This is Austin, Texas, where I live. And this is San Antonio. 4 out of the 5 most populous cities in the state are exactly where we should have not built our cities. And in Australia, to be very honest, it's not any better. So here's the data that I found from you guys. And here you have in blue all the locations where expansive clays exist. So this is a problem, a very significant problem that we have both in Texas, central US, certainly in Australia, I would say all over Australia, and in many other regions of the world. And it has been it's a very, very old problem. And to be very honest, we have not put our hand, as engineers, we have not put together a firm solution to solve this problem until now. And I'll tell you why. But before we get into that, let me try something with you. Okay, I'm gonna ask you, I wanna know who you are. So I'm going to ask you to go get your cell phone or maybe a computer if you have it handy and go to www.menti.com, and you're going to be popped up is a number. Plug in a number. This is the number 29,33,19,9, and I'm going to ask you to answer the following question. My knowledge, your knowledge on geosynthetics is, I want to know where you are in the spectrum of geosynthetics, and it's perfectly fine if your knowledge is not high. So I want to know if your knowledge is very limited, meaning that by very limited, I would say you do not know how to differentiate a geogrid from a geotextile, and that's perfectly fine. Limited, let's say that, yeah, you know how to differentiate a geotextile from a geogrid, and that's it. Intermediate, I could say, I could call intermediate of a professional if you know you can explain what are the different functions of geosynthetics. High, I could say that you have a high knowledge on geosynthetics if you can list the different properties that are associated associated with the different functions of geosynthetics. And I would call it advanced if your knowledge on geosynthetics is such that your knowledge on geosynthetics is such that that you can write specifications about geosynthetics. And I'm playing with my computer, but it's doing something. Let me try something here. Maybe it's not going to work as well as I wanted. Give me 1 second. There you go. Okay, so some of you are already telling me about what you are thinking. So intermediate, high, advanced. I'm gonna give you 15 more seconds. Okay, everybody is an expert. Where are those of you that are not familiar with geosynthetics? 5 more seconds. High, advanced. Okay, a very well-educated audience. All right, so essentially 95% or 85% of you are either highly or educated or even advanced in your knowledge about geosynthetics. So I have some good news for you. The good news is that I am, in this presentation, I am barely going to talk about geosynthetics. And not barely. I'm going to talk a little bit about geosynthetics. But essentially what I'm going to do is I'm going to tell you from the geotechnical perspectives what is the very significant geotechnical problem that geosynthetics will come to the rescue of. So what I'm going to walk you through is going to be a geotechnical tool. I'm going to tell you what is a geotechnical centrifuge. Then I'm going to tell you about a geotechnical problem, and we already started talking about expansive clays. Then I'm going to tell you how to characterize this geotechnical problem, because this has been a very, very important issue. So it turns out that this is a mega, multi-million-dollar problem if we have it, but very often we come up with solutions to this multi-million-dollar problem with tests as simple as plasticity index of clays. And then finally, I'm not going to talk that much about lime stabilization, which is one of the options. And finally, I'm going to tell you about geosynthetic stabilization to solve the problem, not of traffic in roadways, but the problem associated with expansive clays. And let me give you some heads up, it does work. All right, so let me tell you very briefly why I'm going to be telling, how I'm going to characterize expansive clays. And this is a very important issue because, again, we know if clays are highly plastic or no plastic, but how big is the magnitude? What are the design criteria? What do we design for when we have expansive clays? Let me tell you about that. Types of centrifuges. I'm going to be talking about centrifuges, and if you are familiar with geotechnical centrifuges, perhaps you're thinking about something like this, which is a big washer machine where we increase the centripetal acceleration in a model in order so that the model has the state of stresses that corresponds to a prototype. That's not what we're going to be talking about. Instead, we're going to be talking about a geohydraulic centrifuge. This is a type of centrifuge that we have in my lab at the University of Texas at Austin. And essentially, this is characterized by a comparatively high speed, 500 Gs. That's what we want. Gs meaning the acceleration of gravity. Or even a geo-characterization centrifuge, a third type of centrifuge. These are my terms, my terminology. And this is what I call when the priority is something that is expeditious and practical. And it is for characterizing expansive clays. I'm going to tell you how. So this is one geomechanical centrifuge. Actually, I did my PhD dissertation many, many years ago using this machine. At that time, I wanted to evaluate the behavior of reinforced salt slopes, and the goal was to analyze if they fail as we believe that they do, and at the time we concluded that they do fail as we believe that they do. And here we have a view of a reinforced, geotextile reinforced slope. And the evaluation in this case was to evaluate whether the design methods that we have for geotextile reinforced salt slopes are consistent with how we design them. And there are some good news in there, but that's not the point in here. And the idea is that we are going to use a different type of centrifuge. And this is the type of centrifuge that we're going to be using. Again, why are we talking about centrifuges? Because we want to characterize expansive clays. And here is a high G centrifuge. It does have a permeameter inside the buckets. So when we fly this centrifuge, we're going to have a soil sample in there. And we're going to have tons the opportunity to measure many things. And key terms. And again, I know that you are an expert on geosynthetics. You may not be an expert on geotechnical engineering, and that's on purpose. But we can measure aspects such as suction and moisture content and influx and outflux and volumetric changes, the swelling of the clays. All right, so why do we want a centrifuge? Let's say that we don't have a centrifuge. Let's say that we are interested in moisture advancing through this column. And this column is a column that corresponds to what we may call the active zone in a given soil layer. It turns out that the key in here, when we are evaluating expansive clays, I mentioned that this clay swells and shrinks in response to moisture changes. So what we really need to analyze in here is the flow of moisture in the soil under, but, and this is a big but, under unsaturated conditions. If you went to a classic geotechnical program, you may remember flow nets and saturated flow and Darcy's law. All that most likely was in relation to saturated flow. Here we're talking about moisture of flow of moisture under unsaturated conditions. And we have the governing equations for this, and I'm going to show you equations, and that's called the Richards equation. This Richards equation is a little bit of an, and the idea is that we want to infiltrate moisture in this column, and we are going to do it, and we're going to monitor what happens in this column under with time. Big problem. Moisture under unsaturated conditions takes enormous amount of time. And that's why we don't do it. We could do it, but doing one test like this would take perhaps years. And this differential equation is the Richards equation. It's kind of, it's okay because it's a one-dimensional problem, but it's a highly nonlinear equation. It's a very complicated equation to solve. And here are the three variables that matter. One is the moisture content, theta, and the other is the hydraulic conductivity K. We need, if we want to monitor the flow, we need the hydraulic conductivity, we need the moisture content, and this is the other variable. C is the suction. So we need to measure these functions. One is called the hydraulic conductivity function, and the other is called the moisture retention curve. The moisture retention curve gives me the relationship between moisture and suction. The hydraulic conductivity function gives me the relationship between hydraulic conductivity and suction. Hydraulic conductivity is no longer a constant. You may have learned that the hydraulic conductivity is a constant, it's a parameter that is a constant. That's it. It's no longer the case under unsaturated conditions. One other aspect that I'm going to call your attention in this differential equation is this number 1. I'm going to call this differential your attention to this number 1 because this is the number of gravities in this problem. Because we're under 1g, 1 gravity, the acceleration of gravity, this number is 1. Okay, so what the parameters that we want, if we want to solve this problem, the parameters that we need to get are shown here. For a given soil, for each soil, we need 2 sets of functions. One gives me the moisture content versus suction. We call it here the soil water retention curve, SWRC. It's not trivial to get it, and here we get it at different, it is in the horizontal axis, we have the suction, we have different, it's a little bit, it's a nightmare because we need to get different types of tests for different ranges of suction, and for low suctions we use one method, for high suctions we use a different method, for intermediate suctions we get a third method. What about the hydraulic conductivity function? Forget it. It's so complicated to get experimentally that we never get it. We never get the hydraulic conductivity function. Why? Because it takes forever. So forget it. We're not going to get it. But how are we going to solve the problem? We are just going to guess. But I've heard that there are finite element programs and different codes that do unsaturated flow. Yes, but they all have a wild guess on what the hydraulic conductivity function is. Can we solve this problem? Yes, one way of solving this problem is with centrifuge. That's why I'm showing you the centrifuge. Because if we go to the Richards equation again, if you remember, this was a number 1 when we did have and we were not in a centrifuge. Now, if we are in the centrifuge, trust me, this value in here means the number of G levels. And we put a very high number of G levels, and we can do that in a centrifuge. The problem that was take us months, 4 months, 5 months to reach steady state, in this case, will take us 1 day. So now that we can solve the problem, we can run the tests that it takes to get the hydraulic conductivity function. And this is how we can get it, all right? So we can run these tests in a centrifuge. We reach a condition that is very easy to analyze, that is called the steady state condition. And eventually in this test, we impose some variables, the influx, the speed, the rotational speed. We measure the gradient in suction, or we benefit in some cases in which this gradient is 1, and eventually we get the number that we want, which is the hydraulic conductivity. So this is one way of getting the hydraulic conductivity function experimentally from the centrifuge. This is an introduction to what we're going to use next, which is the following: expansive clays. So I told you all that because that knowledge about how to accelerate problems, flow problems in soils in general under an increased gravitational field, we're going to use it now to understand the swelling of clays, which is a flow problem in a very, very low, very complicated soil that is called clay. This is a view of a clay, and here is an electron microscope view of a clay. These are the clay particles. These are little plates. And as a reference, this is the quartz particle. And what makes a clay is that it's tiny. Not really. What makes a clay is that they are negatively charged, electrically charged, and the charge is negative. This is called isomorphous substitution. And a clay is a clay because there is isomorphous substitution. Is a clay because it's tiny? No. Is a clay a clay? A clay is a clay because it has isomorphous substitution. What does this mean? It means that if we have an electrically neutral, and this is a molecule, this is of clay, which happens to be a clay, it turns out that in a smectite, which is one of the nasty clays that we have in Texas and you have in Australia, when this is electrically neutral, it has a bunch of aluminum. And if you remember, aluminum has a valence of 3. Over geologic times, this aluminum in here is kicked out. Is kicked out by what? It's kicked out by magnesium. And they are geometrically a little bit of the same. That's why it's called isomorphous. The same form, same shape. So here comes the magnesium and kicks out an aluminum, and that's happening in the clays over time. But this magnesium has a valence of 2. So for every magnesium that we're getting and we kick out an aluminum, we decrease the electrical charge of my clay by 1. And if we do this, and if we have one aluminum one out of 6 aluminums is eventually kicked out, and we have what is called a monomerilonite, and that's why we end up with this molecule that is negatively charged. It's negatively charged. And how does it satisfy that electronegativity? Well, the way that the clays do it is by stealing the cations that are in the surrounding water. So if we have here a smectite particle and here another smectite particle, the water has cations, and the clays steal those cations. Bring the water in, because I want to steal your cations. And that's how the water, if you put water in the clay, it will suck it out because it wants all the cations that come with the clay, and the clay will swell. And if the water evaporates, that's very easy to come and go, to expand and detract. So if the water is not available, that water is gonna go away. Sorry, but you want the cations, but the clay is gonna shrink because I'm gonna evaporate the water. So that's why there is a lot of ease by which these volume changes can occur, not because we change the size or the shape of the particles themselves, but we change the size and the shape of the interlayer, of the interparticle spaces. Can we measure this? Yes, we can. We have some standard tests, but they take so long. The tests are similar to what we may have done or you may have done when you studied consolidation, but it takes forever. It takes forever. Here's one test on Eagle Ford clay, the clay that I mentioned to you. Here we are 20 days in testing, and here's the vertical axis swelling, in the horizontal axis time, and keeps going and going. And we really, one problem that we have with this test is that we never know when it's going to end. So what's the outcome of this? We don't do them. In practice, we don't do swelling tests to quantify how much the clays will swell. You probably, in Australia, I'm pretty sure that all you do is some plasticity index tests, you make some multi-million-dollar decisions about that, and that's it. And because the other problem is that you do not need one test, you need a battery of tests. You need tests to get what is called a swell-stress curve. So you get the swelling at different, when you tell me the swelling 15% or the swelling of a clay is 20% or 5%, it really doesn't mean much. You need to tell me how much does it swell at a given confinement. So here we have 3 different curves. Each one of these curves led to several months to obtain. And eventually what we want to get is something like this. In the vertical axis, swell. In the horizontal axis, confinement. And the higher the confinement, the lower the swell. And this is the curve that we need. All right, so we talked about water moving into the soils, in and out, and it's a complicated process. It's a slow process. It's a process that we do not have a good handle on how to quantify the properties. Then we talk about laboratory, and we really could do it in the lab, but it takes so long that we don't do it. And when we're going to design, what are we going to design for? Let me tell you what we do in Texas. And I personally think that this is a good, with some deficiencies, but this is a good approach. This is what we do in Texas. The Texas Department of Transportation, TxDOT, says the following. They will run, if you have expensive clays or you're concerned of founding a soil on expensive clays, then you need to determine what is called the potential vertical rise. What is a potential vertical rise? A potential vertical rise is, give me a soil profile and tell me how much this soil profile, the surface of this soil profile will swell if my clay goes from a reasonably low moisture content, as low as you can think that it can get, to saturated. Is this ever going to happen? Probably not. But this is a wonderful index because it takes into account the relevant variables. So it's an index. It's not a prediction of how much it will swell, but it's an index that tells me, okay, how much my profile will swell, heave, if my soil goes from reasonably dry to saturation. And essentially what TxDOT says is, whatever you do, make sure that your PVR, your potential vertical rise, is less than 1.5 inches. So that is less than some 3 or 4 centimeters. That's a lot. 3 or 4 centimeters, but that means that if it is 3 or 4 centimeters, 1.5 inches, you're happy. You can design for that. And if it is more than that, and I can tell you, there are situations and many cases in which the potential vertical rise is 10 inches, and then you need to do something to bring that potential vertical rise to 1.5 inches. That becomes your design criteria. Now I can design. If you give me a design criterion, now I can design. What is the design criterion according to TxDOT? 1.5 inches. As in, we have other design criterions that are problems. Very often we call it factor of safety. Well, okay, for slope stability, I want a design criterion that is a factor of safety of 1.5. What does it mean? Okay, over time, I've done this many, many times. I got comfortable with a design criterion called factor of safety of 1.5. In Texas, they say we're comfortable that we are taking a good handle of the distress caused by expansive clays if the potential vertical rise, an index, a design criterion doesn't exceed 1.5 index. Can we achieve this? Can we design this? Yes, we can. I'll show you how. So essentially, this is a good criterion, in my opinion, good approach, because it has very good practical implications. So there is an outcome that is called the potential vertical rise, and it's easy to grasp by engineers. So what is your PVR here? 1 inch. Oh, you're good. What is your PVR here? 7 inches. Oh, you're really bad. So it's easy to grasp by engineers. It's a concept, a heave in the ground, and I'll show you a real heave. I'll show you, we can measure this. And that is a good concept that is tangible by engineers. Then it really accounts for the relevant variables. What are the relevant variables? The soil characteristics, the swelling of the clay at different confinements, the stratigraphy. If the stratigraphy changes, the PVR changes. The initial moisture content, that matters. The confining stresses, that matters. All those variables are taken into account when we calculate the potential vertical rise, the PVR, and these are the relevant variables. But there are some minuses, some problems with the current implementation of the PVR. In TxDOT, in Texas and in TxDOT, they came up with the right concept, but they arrived to this calculation using correlations because it's so complicated to measure swelling. They said, you know what? Let's correlate swelling with things that we can measure. It's very hard to measure swelling, and let's correlate swelling with things that are easier to obtain, such as plasticity index, such as grain size distribution. So the correlations to achieve that PVR are way too many. There is a correlation to determine the volumetric change using just for a given confinement using the plasticity index. There is another correlation that will get these into what is called the volumetric change. There is another that will make this into a linear, because it's a one-dimensional problem. Another correlation that will transform it into a linear problem. Then there is another correlation that will tell me what is the swelling for different confinements. Then there is another correlation that tells me, okay, I got it, but this is for the typical unit weight of my soil, but it changes if I use a different unit weight. Then they do it, but I remove the coarse particles. So what happens if I have if my soil has coarse particles? Way too many correlations. And even worse, those correlations are too old. They started doing this in the 60s. They were happy at the time, and they kept using the same correlations that they developed at the 60s. It's too little, too old. And that's when the centrifuge comes about. So I'm going to put all this together. Let's characterize the swelling of the clays using a centrifuge methodology. So we have a design criterion, which is the potential vertical rise. We have a technique that is essentially helps me accelerate the infiltration of soil, of water into a clay. That's what we're going to do to characterize the swelling of clay. So we're going to get my soil sample, I'm going to spin it in a centrifuge, and I'm going to get, and the velocity in my sample is going to increase because this is the acceleration that I'm imposing. It's going to be a reasonably small, can be disturbed, can be reconstituted, can be undisturbed specimen. I'm going to place it in my centrifuge a big jump in our technology was when we were able to get this with an in-flight data acquisition system. And more than that, when we do a spin in the centrifuge that I'm going to show you, we do not do one test at a time, we do 6 specimens at a time. So essentially, the type of test that we're going to do is something. This is a centrifuge, it's a floor-mounted centrifuge, and the testing environment is like this. So here we have 6 specimens ready for testing. And what is that we're going to measure? The same thing that we measure in a oedometer test. We're going to measure the swell versus time. But now, if this is the swell versus time that we obtain in a free swell test, in kind of, let's call it oedometer type of test, this is the same free swell versus time that we get in a centrifuge. And while these, we were around 20 days and we were not done, in the centrifuge after give or take a day, we are done with the final swell. And now this is not the end of product. What we really want, each data point of this is one of those tests. What we want is the vertical strain versus confinement. And that's the curve that we need in order to calculate the potential vertical rise. What I showed here in blue are centrifuge tests. Remember, in one spin, we get 6 data points. One spin, one centrifuge, we have 3 of them. So in principle, in one day, we could get 18 points of these. And these red are the ones that we get into using the conventional swell test in an oedometer. And here's another example. This is Cook Mountain, another clay in Texas. This is the test using free swell. This is the test obtained using centrifuge. And this is a second swell stress curve. Again, blue data points are centrifuge tests. Red data points are conventional tests. So we convince ourselves that the technique that we get gives us the opportunity to get this, the vertical strain versus effective stress. And with this, we can calculate the potential vertical rise. So there is a number of benefits. The benefits essentially is that we have a testing procedure that is expeditious, a testing procedure that is highly repeatable. It generates the swell stress curves. It provides a direct measurement of the swelling of clays, which is something that we typically have obtained through indirect correlations. So, okay, correlations for most typically with a liquid limit or with a plasticity index of the clays. So now we can use this to calculate the potential vertical rise. How do we do this? This is an example. And here's a swell stress curve, one of the swell stress curves of one of the soils. This is another swell stress curve of actually, we can get correlations that in the past was so difficult to obtain. So here is the swelling versus vertical stress, which we call a swell stress curve. This is another correlation for a given initial condition. We get how the swelling changes with initial moisture content. The higher the initial moisture content, the lower the swelling. This is another important aspect that we need to define. And this is another correlation. So what is the impact of the swelling of the clay versus, in this case, with the initial dry unit weight of the soil? Different increase in dry unit weight of the soil. If the soil is denser, it makes sense. So everything else being equal, the clay will swell the most. And now we're back to our problem. So we're back to our problem, and now we know how to characterize our clay. So is this road gonna swell? Is this road gonna be distressed with the presence of expansive clays? Well, if we're in Texas, we would say, okay, and by the way, this has been implemented by the Department of Transportation in Texas. Essentially, they will say, okay, let me go ahead and measure the potential vertical rise. And essentially, the mechanism is that the clay will settle, the shoulders will settle, and we will generate cracks along the road. And sometimes when the clay swells, sometimes those cracks will close. But once you generate the crack, even the crack closes, the damage is already there because water can infiltrate now through those cracks and getting into the inner layers of the roadway. And here is the same roadway that I did show you before. This is nearby Texas, and here we're measuring. Here we're measuring in millimeters the fluctuations, and this is not extreme conditions. Here we are measuring on the order of 20 centimeters, 20, so shy of 10 inches of vertical movements, and these are differential vertical movements of the center road of the road to the edge of the road in a one-lane road, 20 centimeters. And this is the type of vertical movement that we do have in highly expansive clay. So how do we do now? But now we can quantify. Do you have a problem here? Let's quantify the PVR. So what do? We are going to run the centrifuge tests in the different profiles. We're going to go to the soil, to the site. We're going to obtain the soil samples. We're going to get the swell stress curves, and we're going to characterize the PVR. In this particular test, the PVR in this clay tells us these are different methods of getting it, but here it's telling me that they have a PVR of 3.8 inches. 3.8 inches is too much and more than what the Department of Transportation requires. You need to bring this down to 1.5 inches. How do we do this? And now is when we are going to try to solve this problem. So how do we do this? We have two ways of doing this. But again, let me get back to how we characterize the problem. First, the first part of this presentation, and it's the main part of this presentation, is, do we have a problem? I do not know. We need to characterize this. And the way that roads are linear features, and along the road we may have locations where the problem is significant and locations where we do not have a problem. And if we stabilize a section with a multi-million-dollar solution and we didn't have to, we're wasting our money. And if we don't stabilize it and we really have a problem, then our solution will not work. So the first step is to double check if we have a problem. And what I've done here is to show you a very reasonably recent approach that builds on years and decades of experience of quantifying the swelling of clays, but now using an approach that essentially is expeditious enough that allows you to build a database of data with which you can design. That was if we have a problem. Let's say that we do have a problem. How do we solve it? There is a traditional solution and an innovative approach. The traditional solution, and I'm not going to spend too much on this, is using lime stabilization. It has significant problems. More than that, it's too expensive. More than that, if you use this PVR approach, you will see that the typical approach, at least in Texas, before they did it rigorously, they could get 6 inches, 15 centimeters. And they will say, okay, let's treat 15 centimeters and we're done. And it turns out that the PVR approach very often tells you, no, you need to treat at least half a meter or perhaps 1 meter to bring this PVR from 4 inches to 1.5. So the fact that you're treating it doesn't mean that you're solving the problem. And the second approach is with geosynthetics. Let me very briefly, what do we do with lime stabilization? You may know about lime stabilization. It has many different benefits. One potential important problem is that it's highly heterogeneous. Remember, what makes this work or not work is not only if it kills this, we kill the swelling, but if we kill the swelling uniformly. If we kill the swelling here in this spot, but we do not kill it at this spot, we're going to potentially even make the problem worse because now we're creating a differential heave, and that's very, very bad. Another important potential problem is if we have sulfates. Sometimes highly plastic clays come associated with sulfates, and if we have sulfates, we're creating a problem that we didn't have to begin with if we add clay. I'm not going to get into the details of lime stabilization because it is a well established with all the benefits and with all the drawbacks that we have, but it's, I would say, the classic solution. And this is what they do in Texas. They really do not know what they're doing. So they say, okay, let's compact the soil to an optimum moisture content. Let's get the target relative compaction of 95%. Let's do what they call it mellowing. They are going to treat the clay outside, and then they're going to let it sit for some time. How long? I don't know. And then we're going to place it, and then we're going to let it cure for how long? We really don't know. And how do you define the dosage? If it is 1% or 2% or 5%, there are some rules of thumb based on the pH that we can achieve, but this pH is mainly to avoid another problem associated with sulfates. It's not really to kill the swelling. So I evaluated in detail the methodology for lime stabilization, and I can tell you, while experience matters, and I'm not going to tell you that the experience not necessarily translates, and what we are doing in Texas not necessarily translates. If it is just based on experience, not necessarily translates to what may work here in Australia. So let me tell you about a new approach, which is using geosynthetics. We don't have time. Okay, so in this case, I'm going to use geosynthetic stabilizations for roadways on expansive clays. And just to step back, and just to summarize where we weren't, I told you about a bunch of geotechnical stuff. I told you about problems in roadways associated with expansive clays. I told you about a technique that requires a very specific tool. It's not a very expensive tool, because even though centrifuges can be very huge, we're using very small centrifuges. But the entire trick is to measure swelling. Essentially, my message in there is, if you're going to design for this, make sure that you have a problem. And if you have a problem, quantify it. Have a design criteria. One of the design criteria that has worked is to quantify the potential vertical rise. And now we can design. Because if you give me a problem and you tell me what do I need to achieve as a designer, now I can come up with solutions. One solution is to excavate and replace. Another solution is to excavate and treat with lime. A third solution is, let's use geosynthetics. Geosynthetics, and let me step back, in roadways can be used for many different reasons, in many different layers, and it can be used for many different functions. And I don't want to confuse you, but I want to give you an idea of how many aspects can be addressed in roadways alone, just in the profile of a roadway using geosynthetics. Geosynthetics can be used for separation. Keep the base a base and a subgrade, don't let mix. We can use it for reinforcement when we develop tensile forces, but we want to minimize problems associated with failure, with rupture of the. We can use it for another function that I'm going to call stiffening. Stiffening meaning, yes, we're going to develop tensile forces, but the objective here is not to avoid collapse or rupture, is to keep a high modulus in my structural package. Those are mechanical benefits. There are hydraulic benefits. Let's filter the soil. Let's not let, if the water wants to get through, let's not let the particles go away as well. There is barrier. I personally do not like it. There have been some experience using barriers in roadways, but in the implementation is particularly problematic. And the one that is very promising as well, but from the solving the problem from the hydraulic point of view, is drainage. But in this particular case, I'm gonna get into one objective. The objective is to retard or eliminate these nasty longitudinal cracks by reducing volume changes due to expansive clays. Actually, the same problem that I'm gonna show you for expansive clays also works in locations that are not Texas and not Australia, but are frost-susceptible subgrade soils. It's the same problem. It's the same problem. It's volumetric changes. All right, so how is this going to work? What we're going to use is, essentially, we're going to use the concepts that are associated with stiffening of the base. Why? Essentially, what we're going to ask the base is to remain an integral unit, even if we have the differential settlements. Essentially what happens, the cracks are triggered because we have a concentration of strains, very high concentration, very stress concentration or strain concentration. And essentially the presence of the geosynthetic, what it will do is it will distribute. The volumetric changes will continue to occur, but what the geosynthetic will do is essentially will distribute that strain over a wide area, and consequently the cracks will not be triggered. And let me show you an example. Here's a geogrid section with no longitudinal cracks, but they use geogrid in this particular case. Here's another test section. The same road, the same traffic, the same weather conditions, give or take, the same soils, longitudinal cracks, one with, the other without geogrids. And the third section, not only with geogrids, but with a reduced thickness of the base, no longitudinal cracks. So based on evidence, we have that, and there's been a lot of evidence that the Department of Transportation in Texas has been using these based on experience, and they tried it, it worked, they kept using it, but essentially now it's only now that we're bringing up a design philosophy, a design criterion for it. So there is significant evidence that it works. Is it gonna work always? No. What design criterion? That's what we're talking about. Let me give you another example. This is a particularly important case study. And what is striking about this is that we have 32 test sections, 32 test sections, and this is a pair of them. And let me tell you, the section on your left is a geosynthetic stabilized section, no longitudinal cracks. The section on your right is a control section. Everything else the same soil, same traffic, same weather conditions, same drainage conditions. Difference is only the presence of a geosynthetic. Let me show you more. This is the results after 32 test sections. In this particular case, here we have this is one way of quantifying this is by measuring the percentage of longitudinal cracks. 60% longitudinal cracks means that over the length of the row of a section, 60% of its length has at least one crack. They could be 200%. That means that over the length of the road of this section, there are 2 longitudinal cracks. And this is control, no geosynthetics. And this is 1, 2, 3 different types of geosynthetics. It's not a surprise that they gave reasonably similar performance, but statistically, there's no doubt that we have, and this is what we call type 1. So these are the geosynthetics that are the least aggressive in order to solve the problem. This is type 1, now we have type 2, and have type 3. 3 different ranges of geosynthetics, essentially the same way that we have different geosynthetics for different problems on soil reinforcement in walls. We have different geosynthetics that address the problem of expansive clays, type 1, 2, and 3. Bad news for the lime industry. Average lime, 64%. To be fair, the way that they do lime stabilization in TxDOT is not that they stabilize. I was telling you that if you're going to use lime stabilization, you need to design for it. In here, what they did is they stabilize the sub base, and they say, okay, I use lime, I'm done. And essentially, by stabilizing the base, the sub base, probably they may even make the problem worse. Let me tell you why. So here's a different way of looking at the same data, vertical axis, percentage of cracks. It's a measure of the distress in the road versus time. Here is geosynthetic 1 and geosynthetic 2 and geosynthetic 3. Are these geosynthetics perfect? No, nothing is perfect. Roads, a good design of a road is a design that designed for a given design life. The roads are designed to fail, but when? At the design life. A road that never fails is a bad design because it's an extremely expensive road. But here we have the case of the increase in longitudinal cracks over one season. Over one season, this went from 8% longitudinal cracks to 65% longitudinal cracks. What about the lime stabilized? here it is. Lime stabilized didn't work very well. The reason is that if you don't do the treatment and kill the swelling, essentially what you're doing is you're transforming, creating a little crust on your subgrade, on your subbase, and this is a brittle crust. So you're not only not avoiding or not killing the vertical swelling, but you're creating a brittle layer that may even trigger cracks that may have not happened otherwise. What I'm not telling you is we need a different property. We need a property to solve this problem, and the property that we have evaluated is a measure of the stiffness. I told you that the property that we need is a property that stiffens the base in a way that it can allow the base will remain stiff even under differential settlements. This property is a property that we have characterized at the University of Texas at Austin, and it's a mouthful, is the confined stiffness of the soil geosynthetics composite. I'm gonna skip some slides and I'm gonna just tell you how to obtain it. And the way to obtain it is using a device, using a device like this. And essentially it resembles a pull-out test, but it is not a pull-out test. It essentially measures the interaction, the stiffness of the interaction under the confinement of soil. This test has been specified in the department draft testing procedure by the Department of Transportation. And the important news is that not all geosynthetics, this is in the vertical axis, the stiffness, in the horizontal axis, different products, 13 products, and not all products are the same. Again, this is not a measure of the stiffness of the product in isolation. It's a mixture, it's a combo that measures the stiffness of the product and the interaction of the soil. But now that we have this stiffness of different products, then we can go back to our case histories and measure how the different products will fare against different case studies. So essentially what we can do now is to go to the case studies that we have identified and define, based on those different case studies, a threshold that will differentiate those sections that performed adequately versus those that did not. So, and we have sections that we consider that they were inadequate. And again, the measure in here was the percentage of longitudinal cracks. So we have case studies that we did not consider adequate. So some geosynthetics were there, but did not perform. It turns out that in give or take, their specific, the KSGC, which is the name of the property, was below 10. And those that performed with higher KSGC performed better and better and better. So not only we can differentiate those that work versus those that do not work, but even within those that work, we can differentiate different levels of performance. And that's why I'm telling you that now we can get geosynthetics of type 1, of type 2, and of type 3. One of the big problems of using geosynthetics in roadways is how to specify. And honestly, because we're specifying based on properties that we cannot put our fingers on, very often this is a previous specification from TxDOT that was based on things such as thickness and percentage open area and junction efficiency, tensile modulus, properties that are dancing around the right thing, but they are not really the properties that matter, that make a geosynthetic work versus those that do not, that make a geosynthetic not work. So the way that this has been modified is essentially now, okay, this is the previous one before this investigation, and now with this investigation, essentially here we have type 1 and type 2. Now we're going to have type 1, type 2, and type 3, but we have a new property, which is the KSGC. And the KSGC, if it is less than 10, it's not acceptable. Type 1 is from 10 and 15. Type 2 is from 15 and 20. Type 3 is about 20. And here's a type 3. All this information is publicly available. This is a report where you can get it, and it's a publicly available report, FHWA, Texas Department of Transportation. And with this, let me wrap up the topics that we have discussed. In this particular presentation, we focused on, eventually we're going to tell you a little bit about how geosynthetics can work. But in order for me to explain, and you to explain why geosynthetics work, we need to understand what is the nature of the problem. What are we designing for? So in conclusion, I showed you some geotechnical aspects, and I know that you are all experts, over 85% of experts on geosynthetics. So let me tell you something about geotechnical engineering. Centrifuge technology can be used to characterize unsaturated hydraulic conductivity of soils. And trust me, that's a very difficult task, made easy with a centrifuge. In particular, can be used to obtain the swell-stress relationship, which is something that we could have obtained if we have a year to spend in the lab, but now we can get it in a day. Now, while more practical and expeditious, the predicted swell-stress curves using the centrifuge is the same. So it has been validated against those long tests. The centrifuge produces the same swell-stress curve as those obtained in these long approaches. The centrifuge approach is particularly appropriate to predict what is called the PVR, the potential vertical rise. This is a practical design. I still call it an index. It has a very important engineering meaning, is how much the ground surface will swell, will heave, if the soil goes from a dry season to saturation. Is this actually what is going to happen? No, typically it's going to go from a low moisture content to high moisture content. So it's going to be shy of the heave that occurs if there is a flooding and it reaches saturation. Okay, that's as far as the problem. So now we know how to characterize the problem. Now, let's go to the solution. Geosynthetics. The use of geosynthetics was found to effectively minimize the detrimental problem associated with expansive subgrade soils. There is plenty of evidence, and this has been quantified and correlated, and it is unambiguous that the use of geosynthetic, the geosynthetic stabilized roadways perform significantly better than those that are not geosynthetic stabilized. One property that we could use for design or for specification in this particular case, in this case, we didn't go over design, we did go over specifications on what works, is the confined stiffness of the soil geosynthetic composite. And it turns out that this property correlates extremely well with a measure of performance of distress associated with the presence of expansive clays. And with this, I have walked you, my dear Australian geosynthetic audience, walked you through a very important geotechnical aspects at the end to tell you that geosynthetics do work and do work very well. And I thank you for your attention.
Perfect. Thank you, Jorge. Very, very fantastic presentation. And I'm sure the audience have enjoyed it as well. So I'll quickly go to Rajesh to have his case study presentation. And then I have received questions, but I'm just a bit time conscious. Let's see how we do with the time and the questions at the end. Rajesh, over to you. Thanks.
Thanks, Mike. Thank you. Good afternoon, everyone. And let me thank Professor Jorge Zornberg for a fantastic presentation, sir. Very informative, I should say, and I'm pretty sure there are lots of debate is going to happen in Australia after your presentation for sure. And let me acknowledge my colleague, Rod 5, who is also attending these particular presentations because he shared his experience and his presentations with me. and I'm just presenting his work here. So thanks, Rod, for sharing the details. What I'm going to do, I'm going to share some 2 or 3 case studies we have been involved in particular Adelaide side of the business or South Australian business, where you will find lots of issues with the reactive as well as expansive clay. And this is the first case studies I'm going to present, which is purely focusing on the paving fabric, which we manufacture here in Australia. The project, this particular section was constructed in 1994 with applying Silmac paving fabric. And just to measure, just to show you some nice photos of this particular project after nearly 15 years of life. So you can see on this particular side, this photo has been taken in 1994 when the Silmac was actually installed. And this is the photo actually in 2009, where it's actually worked very well for after 15 years of life using a wall layer of geosynthetics, just applying as a stress relief membrane in your chip seal applications. This is the second photo, or second project, I should say, with City of Campbelltown in South Australia, which was constructed in 2016, having some typical details of granular fill and also multi-axial geocomposite product was actually used in this particular applications. You can see some photos of that particular project, and the main target was actually controlling the reflective cracking as a result of the very shallow depth of the pavement and environmental factors over the expansive clay subgrade. And as Professor mentioned in his presentations, utilizing different types of the geosynthetics will give you a different performance. So you can see this one actually applicable for these type of applications. My third project, and this is actually the same cross sections with 2016, and this photo is recently taken in 2018, but this was constructed in 2016 with a very good outcome at the end. My third presentation, third case studies is nearly similar application, City of Campbelltown. This is the Chatswood Grove applications reconstructed in 2016. Similar sort of construction sequence utilizing a multi-axial geocomposite at subgrade stabilizations, and main target was actually controlling the reflective cracking as a result of shallow depth over the expansive clay subgrade. And you can see from this particular photo when it was constructed in 2016, before the site condition, before the construction, and this photo was taken in 2018, where a layer of geosynthetic with a granular fill and a very thin layer of asphalt is actually giving a far better results over any other treatment, I should say. So as Professor mentioned, so I'm not going to go in details what he presented, and I think so Professor also summarized very well in terms of utilizing different types of geosynthetics in these type of applications. So you can see, first of all, use of geosynthetics in these types of applications will optimize your pavement support as well as performance. So, very effective in controlling longitudinal crackings. These trials we have done in particular Adelaide areas is showing the proof of crack mitigations. As Professor mentions, that geosynthetic solutions might be a cost-effective solutions compared to other lime or cement stabilizations or chemical stabilizations. And Professor also is talking about the stiffness of this particular granular fill, that instead of actually focusing on the strength or mechanical properties of the geogrids, how the granular fill is going to react with geosynthetic materials, and how it's actually improve the stiffness of this particular pavement layer to mitigate the cracks. We are also focusing on something very innovative applications, which is actually utilizing conductive geosynthetics to gather the stress informations. We also introduced this particular bidding C, which is a conductive geotextiles, may be able to give us some more information or more technologies and solutions can be offered in these particular areas. As Professor mentioned, I'm actually just re-messaging his wording, stating that geosynthetic stabilized pavement can helpful in controlling reflective cracking. Cost-effective solutions are available with a longer design life by utilizing the geosynthetic materials. and new technologies and field trials will have in developing design guidelines. And thanks for my short and sweet presentations. Thanks ACIGS for giving us an opportunity to present this particular initial innovative case studies for you guys. Thank you.
Thanks, Rajesh. So we went a little bit over time in total, maybe a couple of minutes over time. But I really like to ask at least 1 or 2 questions because I can look at the number and still people are staying around. So question for Jorge. So the question is about centrifuge tests giving generally higher values for swell compared to the normal ASTM 4546 method.
Actually, no.
Do you think this is right, or
no? Let me tell you what I showed you. I short-circuited some examples. Essentially, the results that we get from the centrifuge tests are on the spot with what we obtain for ASTM D4546, which is the swelling test. Now, the main difference is time to take it. But let me tell you, maybe this is the reason why the question comes. The example that I presented shows 2 comparisons. One, which is with the centrifuge approach, and the other is not the D4546, is the TxDOT approach. The TxDOT approach established correlations of plasticity index with ASTM D4546. So essentially what it, and I presented one case in which the prediction using correlations, historical correlations, and many corrections gives results that is higher. And I have other examples. If I present a long version of this presentation, I have other case histories in which the prediction using correlations is lower. So my message is, we do not need to use correlations because we can get the actual data and the actual swell data. So when we compare swell data with swell data, the centrifuge data and the swell stress, the data that comes from conventional swelling tests are on the spot. Very close. What is different is if we use the correlations that were developed over time by TxDOT between indexes such as plasticity index. So plasticity index is a good index, but doesn't tell us everything. So yes, there are cases in which the use of those correlations leads to higher, sometimes to higher, which is the case that I showed, sometimes to lower, which is a case that I didn't show. But essentially what we're saying, just get it right. We can get the data.
Okay. And one question I had was also about, you indicated the importance of, first of all, identifying the problem and then quantifying the problem. And that's how we can then get into the problem, to the solution. So you mentioned that, a lot of projects, we say the investigation has a limited budget, and the client is normally asking for limited amount of investigation and trying to use available information or knowledge that is maybe not even particular to that site. However, you mentioned that the centrifuge testing can get the 2 main factors for most of the clients, time and money. So in terms of time, it can get it down from like a test that takes a year down into a day, which is a very good advantage. How about the cost for the testing? Do you think it will also add value in that sense?
Yeah. So let me tell you what we're recommending right now. So in terms of sampling, we need samples that are no deeper than 4 meters. So we're talking about really the area that matters is very superficial soils. You do not need to go to the middle of the road. You can get along the shoulders. So the testing is shallow samples. We request undisturbed, not because we need to test them undisturbed, but because we want to have a good understanding of the profile. So at the same time that we're collecting the samples, we're understanding the profile and how it changes. The testing itself is quick. The equipment, well, I don't know what to say, what is expensive and what is not expensive. I would say it's much less expensive. I want to say that it's not more expensive, actually much less expensive if we consider the time than an odometer test. But an odometer test is days and weeks and months. So in terms of equipment, I can compare it to a, I don't know, some of a triaxial testing or something that is reasonably standard, quick, but typically when we get into these costs of this, essentially what matters is time for getting the testing time, which is quick, and how expensive and difficult it is to get the samples, which is not significant. So
yeah,
it is in the fluctuating area where something is new, is more of a demand and offer, but it is not a complex approach.
yeah, perfect. And obviously it has to be looked at on a project base, and like time, money, and availability of the equipment within the close proximity to the site. So, okay, I want to wrap it up here. I think we had a very, very fantastic presentation today. Thank you again, Jorge. We were actually planning to have you here in Australia around this time. We, got the tickets, everything was sorted. But the pandemic hit, the COVID-19 hit, and we couldn't have you here, yourself and Errol to Tumler. So both of you were planning to do a workshop here. And we really hope that next year is a better year, and hopefully we can have you here around the same time or around the time that the Sydney Soil Mechanic and Geotechnical Engineering Conference is happening in 2021, September, I think it is. So we look forward to that. And thank you again, Rajesh and GeoFabrics, for your support. And thank you to all of our audience who listened to us today. And we wish you a very good time. And good night to you, Jorge. And,
hey, thank you, Rajesh. Thank you, Semak. Thank you, everyone, for sticking around. I really appreciate it. So,
thanks very much.
Very
Catch you later in the next webinar. Cheers.
Bye then.
Yes,
Thank
bye.
you.
Bye.